Week 3 of the user training, and this week is going to be GPU architectures and GPU computing presented by Dr. Andy Getz. And I'll show you the link. This updates about the mailing list. We have one. I've started using it a little bit. I think everybody's on it. I'll do a test today. So if you're in the group today and you don't get an email, let me know. And then we'll add you to it. I use it for announcements, but you can also post a question. And then a little side thing is all questions are welcome because we have many levels of capabilities at participating, beginners to some advanced people trying to remember, who maybe had an account in the 80s or something and now they want to get back on. So all questions are fine, but what I like to do is generally, if you ask a question, if you're wondering or you're stuck, you're probably not the only person. And so I clean it up, I scrub the question, and then I present it, and I send my answer to the whole mailing list. That way we have an archive. If you go to the messages, there's an archive link here, and you can see and sort and view them by date or subject or sender. And all of our questions and the answers are listed and included in the archive. So it becomes productive. But also you can just post a question to the list and don't be too terribly shy, especially if it's on a day when I might not be around to answer a question quickly. So feel free to use the list, but don't use it for shaming. Don't use it for making fun of people. Don't use it for posting political commentary. It's for the class. But do post cool things like, quantum computing presentation in the CSE department. That's also part of the fun of the class, exposing people. Okay. And then try not to send me images. I don't need that. You can cut and paste the terminal text and it will come out in color, and it's easier for me to handle anyway. That way I can cut and paste and scrub information. For week 3, make sure by this point we have created or attempted to create every Expanse account that's been sent to me through that registration form. And so make sure you can log on, okay? And then work on trying to get caught up. I'll begin the process of evaluating. There's no grade, but the way you get your credit, especially as a student for your CCR or anybody trying to earn a certificate from this program, from the center, I have a lightweight grading process, but I do evaluate whether you've done the work. So you can't earn a certificate if you haven't done any of the work. You're welcome just to sit and listen, but also getting your hands in there and working on the material is part of the fun. Okay, so with that, I want to bring in a couple of links and remind you, we have a training repository, and it goes by week, and this week is GPU computing. We are still ironing out some conversion from the old Expanse Comet system to the new Expanse modules. They've upgraded them even since I gave my Expanse 101 talk in December. So the environment is still new and changing a bit. So you want to be in the habit of making sure if something worked last week, you have to ask yourself, well, what's changed? Is it some change I made in my code, or could the system have changed? The sysadmin people try to give us messages like your modules are out of date, and then you have to figure out what that means. But we're updating this, but we do have some examples that do work. And I've uploaded one, and I'll get another one uploaded this morning that I got confirmed working last night. So, and Andy also has some other examples in here that are part of the CUDA toolkit, and we're trying to get that connected. So bear with us and help us debug it. I'm getting a lot of good debugging from messages from you people. Here's our schedule. Like I said, Andy Getz is talking today, and then next week we'll talk about GPU computing with CUDA Python, which is really fun, and then we'll move into OpenMP and MPI. Lots of fun. This is the Expanse 101 tutorial, which you can find by just going to hpctraining.sdsc.edu, and it's got some of my updated material for running Laplacian example is using OpenACC, And then I'm uploading the example for the addition, vector addition. Expanse has a user guide. Between it, our lectures, and this tutorial, you should be able to figure things out and going to links. And then here's the examples for the Expanse 101. And with that, I'll stop sharing and bring in Andy Getz and let him take over. Andy Getz is a quantum chemist, computational scientist at SDSC, and he does a lot of his work in machine learning and quantum dynamics. And I'll let him tell you whatever else brilliant stuff he's working on. Welcome, Andy, and you have the comm.
Hey, great. So welcome, everybody. Thanks for having me and presenting today for you. So can everybody, Mary, can you confirm that the slide is visible?
Yeah, Andy, I can see the slide. I can hear you clearly, and Jeff is recording.
Okay, great. So then,
if people have questions, type them in the chat, and we'll try to answer them as best we can, or save them to ask Andy whenever he's ready for a question.
All right. Yeah. So this is an abbreviated short introduction that's abbreviated from a longer course that I've been giving in a parallel computing class at UCSD, and it's going to be an overview of GPU computing and programming, where programming, so let me go ahead. Yes, we are going to focus on, after looking at GPU hardware and some software examples, we're going to look at, libraries, what libraries are available, then some basics about CUDA C so that you know how you could get started writing a CUDA code, and then open an ACC introduction. So we'll be focusing on what is Nvidia hardware, simply because that's the most widely spread hardware for HPC on graphics processing units, and at SDSC, both in Comet. So the system that's still online, but going to be offline in a few months, and the new supercomputer expands, we have Nvidia graphics cards. And at the very end, so we're going to look at how to get onto the GPU nodes on Expand. So you can see here, some of the slides have not been updated yet. And I have limited experience myself on Expand, so it will be interesting to see if I can get things to work and show you. This also basically shows you, if you don't know how to use the machine, where to get the information and get access to the GPU node, compile CUDA code, open ACC code, and do some benchmarks and so on. So if we get started, we're looking at what is a GPU. It's basically a specialized hardware component, and it's an accelerator. And in the case of accelerators, there's different types of hardwares that can accelerate different aspects of computations. Like in the past, there was like special floating point hardware, and more recently there are FPGAs. If you have some specific algorithms that you want to implement in hardware, and GPUs have evolved basically for processing graphics, computer graphics, rendering of computer graphics, and a lot of development over the last decade, driven by a huge gaming industry, right? So a lot of money has been poured into developing GPUs, and that's why we have this very efficient hardware. Originally, there were like fixed function pipelines to deal with exactly the operations that are required to map to do graphics operations. Modern GPUs are programmable though, for general purpose computations, and that's what we are really interested in. And given their history, though, they have a simplified core design compared to CPU. That's why there is so much compute power available, because a lot of the real estate on the GPU is being used actually for compute hardware, as opposed to some more advanced, say, branch caching features and so on. Partially exposed memory hierarchy. So there's some things that you should know when you program GPUs, and we'll look at these things today. And the question is, why is there such an interest in GPUs? I've been alluding a little bit to that. But so if you're familiar with Moore's law, you know that the transistor count in integrated circuits has been doubling about every 2 years. And so that was an exponential growth, and that growth still holds. But if you look at that plot here, if we look at the transistors, right? So you still have this exponential growth. Now, if you look at the single thread performance, that's been sort of like leveling off. There's still some improvements, but the clock frequency here has been limited, right? So we can't just wait for single CPU core to become more powerful and fast. So instead, the real estate on the hardware is being used to add more CPU cores per processor. So what that means is, basically since 10 years, you have to write parallel code in order to, or even longer, you have to write parallel code in order to make use of modern hardware. And that's not changing, right? It's becoming more and more parallel. In the case of GPUs, you see it's like massive parallelism. Now, actually, let me ask you, can you see a pointer if I move the mouse pointer here? I think there's a way for me to switch.
Yes.
Okay, yes, good. So let me, there's a way to, I'll just leave it as a pointer if that's good enough. And I'll be looking on the other screen, so I'll be not looking into the camera in case that should work. Okay, so what we have here on these two plots is the floating point performance of, in this case, Intel CPUs in blue. Let's forget about the Intel Xeon Phi. It's a little bit outdated, but the trends are still similar over the last years. And then Nvidia and AMD GPUs. And on the left, that's single precision, so 32-bit floating point performance. And on the right, that's double precision floating point performance. And so you see that the floating point performance of GPUs significantly outperforms single processors, right? Where these processors, they are multi-core processors, right? And the same holds for single and double precision. For double precision operations, that's only true for the more expensive data center GPUs, right? So that's one of the things to keep in mind. If you have a code and you can do with a single precision, if that's sufficient for your numerical accuracy, you should exploit that as far as possible, because then you can actually run efficiently on the more cheap consumer-grade GPUs. So there's a significant advantage in terms of floating point operations. The second thing that we see here is the peak memory bandwidth comparison. So that's the memory bandwidth in gigabytes per second of transferring data between RAM effectively to the CPU, or the RAM that's the DRAM that's on the GPU to the GPU processor. And you can see that GPUs have actually also a much higher memory bandwidth. That means you can get data much faster to the processor than on a CPU. And that's very important, because actually nowadays most algorithms are, not all, but it's very typical that you have memory bandwidth bound algorithms, so that the CPU or the GPU is sitting idle, not computing anything, because it's waiting for the data to come from memory to do the compute on, right? It depends, of course, on the algorithms. And if you have very compute-intensive algorithms, you're still compute bound, but very often your memory bandwidth bound, so it's important to have a high memory bandwidth. And GPUs do very well in that respect as well. And of course, how much power do they consume, right? That's very important, because if you get twice the compute power, but you consume 4 times as much electricity, then that's not great, right? But so that's actually not true. You can see that these GPUs, they draw a lot of power, around 250 to 300 watt per GPU, and a typical CPU will draw around 150 watt. So fair comparison is typically a single GPU to a 2-socket CPU server, depending on the CPU and so forth. But that's clearly true if you look at, for instance, here we have a comparison of quite recent x86 CPU versus Nvidia V100 GPU. So V100 GPUs, those are the ones that are installed on Expanse. And we have here the aggregate performance listed in terms of floating point operations and double precision and single precision. And then HP, that's half precision. So the modern GPUs, they actually have specific hardware to support half or even lower precision, special precision types, in particular for machine learning, where it's often not required to have a very high precision. So it depends very much on the application, but you can see that in half precision, that means 16-bit floating point numbers. You get an extremely high floating point performance, on GPUs, and that's simply not possible on CPUs. The memory bandwidth is higher, and then there's something here that's peak PCIe bandwidth. So typically, not always, but typically a GPU, and that's the case on Expanse as well, if I recall correctly, you have the GPU in a PCI Express slot, which means, first you have to load the data from somehow your disk into CPU memory, and then you have to get it onto the GPU via the PCI Express bus, so you're limited by that bandwidth. So that's something to keep in mind. And final question, of course, is very important, is the code that you write portable on CPUs. That's of course the case. On GPUs, you could argue that OpenACC makes the code portable because it's compilable by open source compilers as the standard and so on. OpenCL CUDA, you are locked in some sense with Nvidia hardware. So it's not portable in that sense. If you want some portability, there are other options, or you can use modern frameworks. There are frameworks that basically, you can annotate your code, and then it will generate in the back end either CUDA code or OpenCL code and similar things for you. So there are many different options in the landscape available. So you can certainly write portable code for GPUs. And so if you're looking at those data, right, the data that I've been showing to you, I always like to come back to this. You're looking at a computer that's like, now it's almost 20 years, so less than 20 years ago, the peak floating point performance was 12 teraflops. And that machine filled an entire machine room at Livermore National Laboratory and cost $100 million US 20 years ago. And then, so this is data for Comet. Expanse is more powerful, but you can see it has 2.8 petaflops aggregate performance on Comet. So I don't have the Expanse data here, but you can look that all up on the Expanse website. And a lot of that floating point performance comes from the GPUs. We had like older K80 GPUs, and then the P100s, which is the predecessor to the data center V100 GPUs that are deployed on Expanse. And you can see that on each node, you had a double precision performance of 18 teraflops. It's a single compute node, right? That is outperforming the entire machine, like from 2001. And you can buy a cheap desktop computer. So the RTX 2080, that's the predecessor of the current version of the gaming GPU. So they're really cheap. So you spend $5,000, you get 4 GPUs and the entire computer, and you get in single precision 40 teraflops, right? You have a supercomputer in your desktop essentially, right? So what we considered supercomputer 20 years ago. So there are lots of compute power available, so make good use of it. Now there's lots of GPU accelerated software. So there's examples from virtually any field nowadays. If you go to Nvidia's website, they have a very nice, actually, they have a lot of information about the types of software that is available, and also how these the performance and the programming models that are used, and a lot about software engineering as well. But that's just really to show you that any field you find GPU accelerated software, and of course machine learning has become very popular over the last few years. That's just a single slide that I had added about machine learning, just to tell you why. And when I say machine learning, it's really deep learning that has become so successful because of the compute power that's available in GPUs. And in machine learning in general, what you do is you build a model, a computational model, based on reference data. So you learn based on available reference data. So you have some data, you train your machine learning algorithm, then you get a model, and if that model is good enough, then you can use it. We can iteratively refine it, right? But you can use it for some unknown input data to make some predictions based on that model, right? It's in some sense fitting, right? I mean, you fit something to your data, you have a functional form, and you fit some mathematical function to that. And with deep learning, what you have is these neural networks. And here's a simple neural network that has, input nodes. They're fully connected. Here you have one hidden layer, and then you get some output data. And in a deep learning neural network, you have many interconnected layers. And so, some of the largest neural networks, they have like millions of parameters. And there you can see that if you have a lot of training data, you can potentially make predictions about unknown data with a high accuracy if you have enough learning data. And the key point here why GPUs are so efficient is that if you write out the mathematical equations, how these layers are interconnected, the math, that's all tensor operations, matrix multiplications. And GPUs are very efficient at these because 4x4 matrix algebra is used in 3D graphics. So, the hardware is effectively, ideally tuned for that. And the new GPUs, you can use half precision arithmetic for many machine learning applications, in particular for inference, meaning for the, once you're in the predictive part, so you train in, say, in single precision and or double precision, and then, for inference, it might be sufficient to just use half precision, and then it's really, really efficient. And many machine learning frameworks provide GPU support out of the box, PyTorch, TensorFlow, right? There's not much, you don't really have to know much about GPUs. You just say, I want to run on the GPU, and that neural network model that's been building is going to be automatically compiled for the GPU. Right, and so I'll show you some benchmarks, and I always like to put this up here, comic, where, Dilbert comic is there still, but do you have the benchmark results? And Dilbert says, do you want the 10-minute explanation of why the data are useless, or a simple, here you go? I'm in sales, well, here you go. So you have to be careful a little bit with benchmarks. People always show the best side, and it always depends on what they compare to and how they have compiled the codes. And so there's a lot of cheating sometimes going on with benchmarks. So that's just one thing to keep in mind. And I'll just want to show you two examples from my own research field, because Mary already told you. So my background is I'm a computational chemist. I develop methods and use methods in quantum chemistry and molecular dynamics. And so we already, a few years ago, we edited a book about electronic structure calculations and graphics processing units. So that's one of the fields where GPUs have been successful, although it's very hard actually to write efficient code for quantum chemistry applications or electronic structure calculations on GPUs. So that's an example of the Terrakin code that was one of the first codes, and the comparison to games. And this is a very old plot, but you get the idea as, that compared to a single CPU core, you got very, very large speedups, or the time to solution is much lower, right? There's one example here, instead of 3 hours, you wait just 1 minute for the solution. And we are also developing a open source quantum chemistry code, and similarly here, you have comparison of the single GPU time here, that's in red, and this is a logarithmic scale, for two pieces that are most expensive in these density functional theory calculations. And you can see the time that's required on the GPU here with the dashed line for the two parts of the calculation, and in comparison to the MPI parallel calculation. So, easily outperforming a single compute node on a single GPU. And some of these things you have to think very carefully. It's like with all parallel computing on how to decompose your data so that you can, in a data parallel fashion, work in parallel on the data, right? And for instance, here, this is just an example is the numerical quadrature that we're doing, where we have a lot of grid points, numerical grid points, where we compute function values for numerical integration. And then we partition that with an octree-based algorithm and distribute the grid point patches onto effectively all the many compute cores that are available on the GPUs, so that, you know, we have like hundreds of thousands of these grid points, and then, you know, if we have like many thousands of compute units, you can in parallel operate on those, and with that, you know, achieve a significant computational throughput. See if this works. Oh, this is just molecular dynamics. You know, we simulate molecules interacting, and we have to compute all the atom-atom interactions, many of them. So we have like tens of thousands of atoms, and then, you know, they all interact with each other, and we need to compute many time steps in order to compute the dynamics of molecules, biological molecules in this example here. And so we need to compute millions of time steps. So each of the time steps needs to be sufficiently short, you know, cannot take much time. Otherwise, we would have to wait too long for the simulations to finish. And you can see here some of the benchmarks of this, the AMBER molecular dynamics code that I was involved in developing the GPU accelerated implementation. And this is a measure of the performance that you get here, for example, for a cellulose strand simulated in water with 400,000 atoms. And you can see, so larger is better, is faster, right? So effectively in a single, this is an older GPU now here. It's like 10 times as fast as a 36 core CPU-based compute node. So you get a single GPU in this case, even a performance that's as good as multiple compute nodes with CPUs. And of course, it depends how well the CPU code has been optimized, but that's, you know, we have a CPU code that's reasonably optimized, and the GPU code, of course, as well. And you can see that newer GPUs significantly outperform some of the older GPUs. And one of the things that we did in this code is we did a lot of effort to implement algorithms in single precision without sacrificing numerical accuracy. And that's the reason why we can, in addition to this data center GPUs, we can also run very efficiently on cheap gaming GPUs. So I talked a lot about, you know, a little bit about hardware and some of the software applications. And now the question is, you know, if you want to use GPUs, I did my part about reading about GPUs in a trade journal. Now you do the software part, and then, you know, manager comes back, why is your part taking so long? So it can be simple if you just use libraries, but if you have to implement something from scratch, it can be complicated. And so if you look at the GPU versus CPU architecture, so on a CPU, so if you think about that's the real estate that you have in terms of like space on a silicon chip, right? That's a very rough comparison of CPUs versus GPUs. So on a CPU, you have a lot of cache memory and arithmetic logical units. That's where the compute happens, and then you have a lot of control units that do a sort of like prefetching, branch prediction, lots of smart stuff for you. And you have much less of that on the GPUs. Instead, you have thousands of simplistic compute cores, right? And they are grouped into a few multiprocessors, right? And these operate in lockstep. So, you know, you have to know that they do the same operation at the same time. So if you have two compute cores here on a CPU, this one's very happy doing something completely different from this one. That's not the case on the GPU. So you have to make sure that, you know, you do vectorized load stores to memory, and that you have a data parallel implementation where you don't have a thread divergence that, so branching basically, you have to avoid that. And you need to manage some of that memory hierarchy yourself. That's an example of how a GPU architecture looks like, and it still essentially looks the same. So 10 years later, the basic architecture is the same. You have multiprocessors. So one GPU will have many of these multiprocessors. And so each multiprocessor has many single precision and double precision compute cores, right? So the latest hardware has, I believe, 64. So the V100 has in one multiprocessor has 64 compute cores. Okay, and a few special function units. So if you alluded, that's another thing. If you use a lot of like special functions, like transcendental functions and so on, similar like on a GPU, they're more expensive, right, to compute. Then that instruction cache, shared memory is sitting there, and that shared memory, in order to write efficient code, you'll have to often use that explicitly in the code yourself. So you have to use that. It's a little bit like writing cache efficient code for CPUs. And one thing to know is in order to hide memory latency, so the latency that's involved with fetching data from the global memory. So here's the DRAM to the processors. The multiprocessors can handle many more threads than they have processing cores. So that's very different from a CPU where you don't want to launch more threads than you have CPU cores typically. So you have, 32 cores. You want to run 32 threads. On a GPU, that is different because there's hardware that automatically handles that for you. So you can, and you should launch many more threads than you have actually compute units available. That's some history. Don't have to talk much about that. OpenCL has been around since 2008. CUDA has been around since 2007. Then there's CUDA Fortran as well, and in 2011, OpenACC was introduced. CUDA is based on something older that's called Brook, so I think that's not very important to mention here. And so the advantage of OpenCL is that that's a standard that works both on Nvidia and AMD GPUs and other devices too, by the way. But it's typically less efficient code that you write on with OpenCL than CUDA. Then there's CUDA Fortran. So there are extensions not only for CUDA C, but also for Fortran. That has been implemented in the Portland group compilers. Portland is part of Nvidia now, so you can get those compilers for free. I'll talk a little bit more about that as well. And then OpenACC, that's also interesting, particularly if you get started, because that's like OpenMP-like compiler directives, both for C, C++, and Fortran. And it's designed to make porting GPUs easy and quick. So it's supported by the PGI compilers. And then, so NVIDIA has a toolkit. So you can get those compilers for free from NVIDIA. And then NVIDIA has an HPC toolkit where they have their own compilers now, which is effectively building on the PGI technology. It's also partially supported by GNU compilers. And I've never tried it with the GNU compiler, so I cannot vouch for how efficient those are and if they support all the features of OpenACC. And OpenMP itself, starts to introduce basically accelerator and vectorization directives. Again, so from what I know, it's not yet as mature as people would want it to be. So the idea is that you write OpenMP directives, and you can use those to generate CPU code and GPU code and so on. But I think the portability is there, but what I've seen in recent talks is the performance portability is not yet there. So you write code in OpenMP that works well on the CPU, but then it won't run well on the GPU and vice versa. And how does a CUDA code look like? I'll come back to that. So let me see, it's 1:40. We have a total of 2 hours, so I'll think, yeah, I just want to make sure that we stay on time and track. There's a lot of slides to go through. What you do, so this is just a very basic, to give you the inside is the idea of how CUDA works. So you write kernels, that's source code that then gets compiled into code that executes on the GPU. And you can launch those kernels from the CPU. So that's a key thing. So you have a kernel here. That's a function. And underscore, so this underscore global underscore declaration specifier says this is a global function that runs on the GPU but can be called from the CPU. And the key is you have copy operations to copy data from CPU to GPU memory and back, and you can pass pointers into those functions from the CPU, so you can tell the GPU which data to work with. And then you just write effectively serial code, and that kernel gets executed in parallel on many different threads. So you tell it when you launch it on how many threads, and then internally there is some information that the GPU keeps track of via CUDA of the index number for each thread that is running, and with that, you can address different elements in an array, for instance, right? So you have an array A, and you want each thread to work on a different element of the array. In this case, increment the value by 1. And all you have to do is you have to compute a unique ID for each thread. And each thread runs that same code, but has a different ID, so operates on a different data element. And that's literally how you parallelize with CUDA. I'll get back to that. Yeah, so if you had something like this kernel, right? That's a C code. So for people who are familiar with C, then you'll have a main program, and you can define the dimensions here of, in this case, 16 by 16. You know how many bytes you have, and then there's some regular C code, and there's a CUDA malloc function that allocates memory on the CUDA device, and you want to allocate memory so that you can store the data that you want to operate on in the GPU memory. And then here's a CUDA memset function that basically sets that memory element all to 0. And then you can define here so-called kernel launch configurations, and this basically tells how many threads you're running in parallel. I'll get back to that, but this launches the kernel, and then this kernel here is going to execute on the GPU in parallel on a so-called grid of threads with a certain number of blocks, and each block has a certain number of threads that you have defined here. So we have 4 by 4 threads in each block, and then we have a grid that, in this case, we launch like 4 blocks, 4 by 4 blocks. And so then you copy the data from the device to the host, so you've done your operations, and then you can check the result. And so that's the general workflow, and we'll get back to that. Then thinking about the hardware characteristics change. It's not a problem, right? So you have different number of multiprocessors and so on, but you can query the hardware via the CUDA libraries, and then you can just execute and launch the kernels with certain settings depending on what type of GPU you're running on, right? So how many threads do you want to launch, right? So you do that at runtime automatically. So you can write portable code that runs on multiple different GPUs and different GPU generations, actually. You'll have to know a little bit about, CPU and GPU memory, and then that there's global memory and the different types of memories that you have available on the GPU. There's something called unified memory. So you can program a GPU with CUDA using unified memory, and then the CUDA library handles all the memory transfers for you under the hood, and you don't have to worry about whether a pointer is on the GPU or the CPU and so on. Of course, if you don't do it correctly, that will have performance implications because the data still has to be transferred between the device and the host. And then, of course, yeah, Nvidia is different from AMD. And I personally don't know much about AMD. Yeah, let's go through this very quickly. So like I told you, the hardware, the way it's designed didn't change much, but certain hardware features changed, right? So, the early data center GPUs, they had a double precision to single precision performance ratio of 1:8. And then it was 1:2, similar to what you have typically on CPUs, right? And then there was a data center GPU, the K10, that has a double single precision ratio of only 1:24, right? So if you really rely on double precision, that would not be a good GPU for you. So these things have changed a little bit over the time. And I have here the V100 on here. That's the type of GPU that we have on Expanse. And so if you look at the last column here, that's the most interesting one. So you have 80 multiprocessors on one of those GPUs, okay? And each of those 80 multiprocessors has 64, we could call it like single precision cores, right? So you have 80 by 64, that's 5,120 cores. So you can run literally 5,120 threads in parallel doing compute. And as I said before, you want to launch many more. So you really need a massively parallel problem, data parallel problem, to efficiently execute that on a GPU. And yeah, so double precision performance is 7 teraflops of a single GPU. Then there's something here called warp size. That's the number of threads that actually operate in lockstep in each of those blocks that I had mentioned before. It's a little bit confusing, a lot of information, but that's just something for you to know, that whenever you write kernels, you always want to launch them in multiples of 32, otherwise you waste computational resources. Then, the different GPU models, they have different compute capabilities. You can look that up. There's different hardware versions, and depending on the hardware version, you need a corresponding CUDA toolkit with a corresponding compiler and libraries that support that hardware version. And so we have hardware version 7.0. That's the Volta V100. 7.5, the Turing architecture. So there is no, well, there is data center GPUs, but they're mostly built for machine learning inference. And then the latest hardware that just came out recently is the so-called Ampere architecture. That's the Tesla A100, for example. But there's also consumer-grade gaming GPUs, effectively, cheap ones. And so they introduce like certain new features with each new hardware version. For most parts, we don't have to worry a lot about that. So what you have to think about it, so you never write a code with any assumption for how many threads it will use, right? So you just query the hardware in your source code, and then you launch the kernels with a corresponding configuration at runtime. And what you want to do is you launch many more threads than you have processing cores available. And for data types, if you can avoid double precision, do it, because you'll get much more performance. And you can run very efficiently also on gaming GPUs. As an example, right? I mean, you have to spend something like on the order of $10,000 for a good data center GPU, and you can get, a equivalent gaming GPU that has the same single precision performance for, I don't know, $600. Okay, that's the programming languages I mentioned before. We'll be looking at CUDA and OpenACC. Yeah, the accelerator directives work for Nvidia and AMD, but not with implementations that are owned by Nvidia. Okay, so the PGI compiler used to support AMD until it was bought by Nvidia. But in principle, the open source, OpenACC is a standard, and the open source implementation should support both Nvidia and AMD GPUs. Now, okay. So if you look at the Nvidia GPU computing universe, so good sources, if you have that link down there, you can look at the CUDA C programming guide. It has a lot of information and probably, if I recall correctly, some other links from there, how to download the CUDA Toolkit and so on. And this is taken from the CUDA C programming guide. So literally you have a GPU applications, and so you can work with libraries. Like there's libraries for deep neural networks, other libraries like QFFT for fast Fourier transforms, CUBLAS, that's the basic linear algebra systems, if you know, the equivalent to the CPU BLAS function. Magma is another linear algebra library that also implements, let me think about what they implement BLAS-like functions, also for multi-GPU support, and then a linear algebra problems, solvers for linear algebra problems. And there's many more libraries. And then you have support for C, C++, and Fortran, and then there are wrappers for Java, Python. I'm not very familiar with those. And directive-based computing with OpenACC, okay? And all of these, they support all the different types of GPUs. So if you have a GPU in your laptop, even if it's an Nvidia GPU, you can program on that and run CUDA code on that, right? So that's actually quite neat. So you don't have to have access to an expensive data center to actually develop code, right? You will want to benchmark it there to optimize it, but you know, you can very well develop on your just simple desktop computer or laptop. The CUDA toolkit is free. You can get it from Nvidia. It contains the CUDA compiler and VCC, which is a compiler driver that drives, you know, both the host compiler for the C or Fortran code and the in this case C or C++, and the CUDA compilation of the kernels. Has a range of development tools, so there are debuggers. There's like so CUDA GDB, CUDA memcheck. So this should be a comma, I think. So this is CUDA GDB, and then profilers NVProf and NVVT, and then so these are being phased out. They're still supported, but Nvidia has new profilers. I've not been using them myself much, so I keep forgetting their name. There's basically two compilers that give you the information that usually used to come from NVProf, and you can dig into really what all the kernels are doing when they are running. There's an IDE for Eclipse and Visual Studio, and then you get a wide range of libraries, and then CUDA code samples, which are very interesting to look at. We'll look at those a little bit as well. All right, so like I said, so we have an application, and how can we make use of GPUs? If you can use libraries, because that's basically a drop-in replacement. If you have code that you know is limited by, you know, matrix multiplications or things like that, like BLAS. If you have BLAS functions, you can directly use CUBLAS, which is the CUDA implementation, and that's going to run on the GPU. Then with OpenACC, you can easily accelerate applications with a directive without having to write things from scratch. You, of course, have to think, and you know, it's never as easy as just inserting directives and everything works fine, but that's the principal idea. And then, you know, with the programming languages like CUDA, you have maximum flexibility and best performance. So that's the first thing that we'll look at. I'll show you one example on what you would do if you have a source code that does something computationally expensive, uses a standard library, and then you want to use the corresponding GPU library. Okay. So that's of course easy to use. You don't have to know anything about GPU programming really. You just follow the manual and that's it. And many GPU accelerated libraries follow standard APIs, so that's pretty good because it requires minimal code changes. And they are high quality implementation. So anything that's once it's in a NVIDIA library, they typically work very well. So they're highly tuned. If there's something available, don't try to write the source some code for a matrix multiplication or something like that yourself, because you'll never get the same performance. So use them if you can. There's a list. I already mentioned libraries, lots of math libraries. Yeah, just look around. You know, if there's anything that you think you might need, it's likely that there's something that's already out there. There are also like newer libraries that are for parallel algorithms, right? For collective communications, NCCL, the Nickel library, and so if you have more advanced parallel computing across multiple GPUs, if you're getting into that, so there's lots out there. And so, looking at a simple case, what we're going to look at, so imagine you have a function call that's SAXP, S-A-X-P-Y, that's actually a single precision, that's a BLAS function. It's a single precision A times X plus Y, where X is an array and Y is an array, okay? And so you just replace that with a call to CUBLAS SAXP, effectively. You have to manage data locality, so you have to move the data from CPU memory to GPU memory. There are C functions for CUDA malloc, CUDA memcopy, and so on. And with CUBLAS, there are special functions for, you know, CUBLAS set vector and CUBLAS get vector. You just have to look into the, you know, the manual that defines the application programming interface. And then all you do is then you recompile with NVCC and link it against the CUBLAS library. That's it, right? Instead of linking against, say, the BLAS library, you link it against CUBLAS. So that's an example where you have 1,000,000 elements, n equals 1,000,000. Again, so this is C, and then you call the SAXP function. So it literally does that. Vector y equals, you know, basically you're adding A times X to Y. So that's why it's called AXPY. And S stands for single precision. There's also double precision version. And so that's the API for the BLAS function. So you could find something like that in your source code. N is the number of elements. 2 is that constant A, and then dx and dy are the arrays X and Y, and that's just a stride, right? That you have to define in the BLAS function. So that's how the SAXP function call looks like on a CPU code. You often will find something like D underscore and H underscore. That's actually wrong. This should have an H here. Sorry for that, but it's not very relevant. But often you find that in the source code that programmer will prefix variable names D for device and H for host, where host is the CPU and D is the device, is the GPU, so that you don't forget which variables in your source code actually are pointers to GPU or CPU memory. So now this is correct. So we have device pointers here, and that's just the function called for CUBLAS SAXP. So you just replace BLAS with CUBLAS SAXP call, and you have to pass it a handle that has some information about the some data that's being initialized on the GPU for the CUBLAS functions. And so you add this CUBLAS create, and then you destroy that handle at the end. So that's really literally something you can just look up in the manual. You allocate memory for the device pointers, so you need space for that array on those arrays on the GPU. And then there's a CUDA free function that then releases the memory again. And CUBLAS set vector is really transferring the data to the GPU. And you basically just say that you have n data elements, and you copy them from X to D. And then CUBLAS get vector does the same thing. You copy them basically back from D to Y. You don't have to use the set vector and get vector functions. You could do it with CUDA memcopy, but you know, that's just for convenience in the CUBLAS library functions available. And that's it. That's really it. Yeah, and then like you compile the code with NVCC and you link against the CUBLAS library, and that's it. Right. So what happens then when your source code runs? You'll allocate memory on the GPU. You'll transfer the data from the CPU to the GPU. The compute happens entirely on the GPU via the CUBLAS library. And then when you're done, you transfer the data back to the CPU. Okay. And if that was your compute intensive part in your application, you have basically accelerated that by using the GPU. Okay. Let's go through CUDA C basics. Now make that very quick. I know that if you've never seen it before, it's going to be hard to maybe follow, but I hope you can follow and maybe at least get some insight. So get a lot of information here on this website. I hope that that link didn't change. But in any case, if you Google for CUDA, you'll find all the information. So CUDA C, that's what we're going to look at. That's the solution to run C seamlessly on GPUs or C++ as well. And I would say it's the de facto standard for high performance code in Nvidia GPUs. It is Nvidia proprietary, but it's an open standard. They've made open, so I mean it's not going to go away anytime soon. There are modest extensions to C or C++, but still, you know, requires major rewriting of code and thinking about how to structure the code to express the data parallelism and write code that is efficient. Right? It doesn't only have to run on the GPU; it has to run efficiently on the GPU. Then the CUDA Toolkit I already alluded to, get for free. And well, then there is CUDA Fortran, which supports basically CUDA extensions for Fortran with a PGI compiler, or the compilers that are part of the Nvidia HPC SDK. Can have a look at the CUDA programming guide. It's pretty good as well. It's not too hard to read, or you know, there's lots of books. There's probably newer books available now. If you just Google for them, I used to use those books for introductory teaching and learning of CUDA. They're pretty good, but there are many other books out there. And often you'll hear about heterogeneous computing. That literally means you have hardware that's heterogeneous. You have a CPU and a GPU, and you know, typically that's how it looks like. You have a serial code that executes on the CPU. That's the host, and then you have your device functions that you call from the CPU, where the kernels are being executed in parallel on the GPU. I copy data back, you do some more operations on the host, and then you call again the parallel code on the GPU. So that's what typical CUDA code looks like, okay? And so the processing flow is, you have the CPU, right, and your CPU memory, and then you copy your data from the CPU to the GPU memory. So that's the device here, right? So you have here these multiprocessors. And so first the data lands in the DRAM here in that what's called global memory on the GPU. And then you load your program. So you call the kernel. And so the CPU gives the instruction, hey, launch that kernel. And the kernels, you know, start basically running some compute. And so they load the data from the GPU memory. Can cache it on the chip for performance, so that's the shared memory and so on. And then when you're done, you copy the results from the GPU memory back to the CPU memory. Okay, so that's the general way how the processing flow is of CUDA code. There is, I mentioned this unified memory. So if you use unified memory, that's a pooled or managed memory that is shared between the host and the device from a programmer's perspective. Of course, there is still, hardware you have the system memory that's sitting on the motherboard, right? And you have the GPU memory that sits on the GPU card. So, and you have to transfer data between the two. And of course, the GPU can only access data. So the processor here only on the GPU memory, and the CPU cores only on the CPU memory. They're the system RAM, right? So this is primarily a productivity feature, which makes it easier when you start to get with programs. But the memory copies still happen under the hood and so you have to be a little bit careful with respect to performance and what's happening. Eventually, typically people develop with unified memory, and at some point then they'll just switch to manually managing the memories to have more control over what's actually really happening. Now, there's some definitions. So the kernel is just a function, some code and a function, typically a function that can be executed on the GPU. It's just a nomenclature, and the kernel code operates in lockstep on the multiprocessors of the GPU. I already mentioned that. And it happens in so-called warps. So there's always 32 threads that will do the same operation at the same time. If you think about it, if you have only one thread in those 32 that has an if statement and does something else, then the code gets serialized, which means all the threads do one branch and then all the threads do the other branch. And that means that one thread stays idle and then 31 threads that stay idle. So that's something you want to avoid. And a thread is just an execution of a kernel with a given index, right? So you can index, each thread knows its own index via built-in variables in CUDA. And you can use that to access a subset of data to operate on. And then the threads are grouped into so-called blocks. And the thing about the blocks is that threads that are part of a block are guaranteed to execute on the same multiprocessor. Okay, that means they have access to the same shared memory on that multiprocessor. And that means that the threads within that block, they can communicate with each other and exchange data via that shared memory, but not across different blocks. And then you have the grid. That is the number of basically all threads that are running. So that's the collection of all the blocks. And it's just for convenience called like that because, this way you can understand how the grid of blocks maps onto the underlying GPU hardware. So the number of threads per block times the number of blocks gives the total number of running threads at the same time. Right? That's just for the nomenclature. That's an example here. That's a visualization of a grid that has a two-dimensional grid that has two-dimensional blocks. With two-dimensional, I mean, it has an index that's composed of two numbers. I'm sorry for this, it's a little bit grainy. It's copied out from the CUDA documentation, online documentation, I believe. And something happened with the graphics quality. So the grid runs on a GPU, right? So you launch a grid of thread blocks. And each block maps to the multiprocessors, right? So like I said, they never split across multiprocessors. So if you launch only one block, you will all those threads will only run on a single multiprocessor. So in this case, we have 6 blocks, right? They have index 0, 0, 0, 1, 1, 0, 1, 1, 2, 0, 2, 1, okay? So if you have 6 multiprocessors, these can each run on a different multiprocessor, right? If you only have 2 multiprocessors, then the GPU will automatically distribute them across the different multiprocessors, okay? And then each block contains a certain number of threads. In this case, like I told you, it should have at least 32. So that's not a good example, but that's just for visualization purposes. It would be 4, so 3 by 4, so 12 threads, right? So in this example, simply So each thread then gets mapped onto a streaming multiprocessor, so a GPU core, right? And all of those threads, they will be on the same streaming multiprocessor. So they're guaranteed. So these threads within that single block, they can all talk to each other via shared memory. Okay. And so 32 of those threads will execute in lockstep. Okay, that's simply what happens. So if you have 64 threads in a block, you can have the first 32 operate in lockstep and then the next 32. And there's no guarantee in which order they will execute. That's one thing to keep in mind. Now, then we have built-in variables that allow you to compute the ID of each thread that is executing on a grid block. So grid dimension, and so grid dim Z is unused, so you can have a two-dimensional grid, but you can have actually three-dimensional blocks. Now, the reason for that is that it's often convenient if you have problems. So if you have a linear problem, say you have a vector, right? Then maybe you only want to have a one-dimensional block. As for indexing convenience. If you have an array, a two-dimensional array, a matrix, you might want to have a two-dimensional block, because then you can say, okay, thread 0, 0 operates on matrix element 0, 0, thread 1, 0 on matrix element 1, 0, and so on. It's just for programming convenience. And then you have variables that return the grid dimension, so the number of blocks in the X, Y, and Z axis. Right, and that's the ID of your block. And then you have the block dimension, that's the number of threads within a block. And then you have the thread ID for each running thread. And what that allows you is to compute the size, the number of total threads running at runtime, and the ID of each thread. And that effectively allows you to address data in your CUDA program. All right. Let me see. I have to see what else is coming up. Yeah. I don't have a lot of programming examples. I will very quickly go to a complicated example, and I'll just briefly show what happens with more complicated matrix multiplication example. So then we have that global keyword that is a function that executes on this device. It must return void. This called from the host code, right? So you could have, for instance, a vector addition kernel, where what you want to do is basically you add A and B and store it in C. And A and B are vectors, and C is the result vector, right? And the way you would implement that is you pass the pointer to those, vectors, to those arrays, and the total number of elements, right? And you know that you have a fixed number of threads that you launch, a fixed grid size, with a fixed number of blocks and a fixed number of threads for each block. And so now what you do first is you compute the ID of each thread, right? So that's basically the ID of the thread. So I'm assuming here I'm just using a one-dimensional grid of blocks and a one-dimensional threads in a block. Okay. So that's my thread ID plus the offset of the block ID, right? So if my thread is in the second block, and each block has 32 threads, then I know that my ID is going to be my thread ID within that block plus the offset of the previous block. And then you can compute a stride, for instance, that's the total number of threads that are running. So that's the grid dimension times the number of blocks. That's basically the number of blocks. That's the grid dimension times the number of threads in each block. That's the total number of threads. And then you can do a loop and say, so each thread starts with its thread ID. If it's smaller than n, right? Because I only have n elements in my vector. If that's the case, then I load that data, A and B, add it and store it in C. Then I increase my ID here And I keep doing this until I'm out of the range for the array that I am working on. That's how you would implement a vector addition on a GPU. Okay, for an arbitrarily sized vector with a fixed number of threads, and you could launch this with, say, I don't know. Typical is something like, say, 256 threads per block, and then you launch, I don't know, 64 blocks or something like that, and with that, you know, you have 10,000 of threads operating at the same time. And so then you will have to have the CUDA API handles device memory, so you can allocate memory, release memory, copy memory. That's from the CPU to the GPU, and that's just equivalence from to C functions malloc free and memcopy. Okay. And then you have this kernel launch specification that's in this triple angle bracket here. And literally that just determines the grid and the block size that I just was talking about. So you call that kernel, right, that we've just looked at here. And you tell it to launch a grid of bx times by times bz blocks, right? So if I have only one-dimensional blocks, I only need to specify bx. I could say I want 64 blocks, so I put 64 in here. And I also want a one-dimensional blocks, so say 256 threads per block, so I put a 256 in here. And then I pass the pointers to the corresponding device memory for the vectors A, B, and C, and the size, and that's it. And then the GPU goes, launches that kernel with thousands of threads and does the compute for you. What you have to make sure is that your launch configuration and your function call matches what you have implemented here. Then a few more things that I talked about this before. I just want to emphasize this again. So you have the host memory and GPU memory. I'll talk quickly about the different types of memory. So the global memory here, you have that here. The device memory, that's visible to all of the threads, right? They can read and write. It's faster than the CPU RAM, right? I've shown you that in some of the very first slides, but it's still a relatively slow memory. So memory access here still takes hundreds of clock cycles, okay? So latency is large. And then you have the shared memory that's sitting on a multiprocessor, and like I said, so each block has access to the same shared memory, right? And that's visible to all threads in a block, and that's fast on-chip memory. So that's why you want to cache data in the shared memory if you repeatedly operate on that. And then, of course, there's a certain number of registers that get allocated for the variables in your code, and these are visible only by each thread, of course. But, then there's something that's confusingly called local memory. It's called local memory because it belongs to each thread, but it's actually offloaded into global memory. That's when you run out of registers. That's slow. So that's what people call register spilling, and that's bad if you have that. So that will slow down your code. And then there's something that's called constant memory. That's quite useful, so you can upload constants, right? I mean, if you have something like, I don't know, natural constants that all the threads need at the same time, and that's very efficient to access if all the threads need the same data. You can upload data into constant memory from the host. So that's why it's called read-only. It's from a GPU perspective. The GPU processors can only read data from the constant memory. That's why it's constant. But you can modify it from the CPU. So you'll have these general programming strategies where you want to avoid data transfers between CPU and GPU because these are very slow because they go through PCI Express bus. Even if you have some more expensive data center GPUs and other technologies, that's still relatively expensive. or slow. Then you want to minimize access to global memory, and one way to do that is automatically, in some sense, by the CUDA architecture, is by launching many threads, more threads than you have actually compute cores on the multiprocessors. And what CUDA does, it launches a block, and while that block is waiting for data, you can have another block doing some compute on the processor, actually, right? So if you have more than, excuse me, one block running on a single processor at the same time, that's the way that memory access data latency is hidden. Right? You parallelize effectively in time compute data loads and stores. And then what I mean here with take advantage of fast shared memory by tiling data is very similar to cache blocking on CPUs. So you partition data into subsets that fit into that shared memory that I mentioned. And then each thread block handles a subset of the data, loads that subset from global to shared memory using multiple threads. And then you perform computations on that data subset in shared memory. And then you copy the results back to global memory. So to avoid multiple global memory reads and writes, okay? And we'll see if I manage to explain this properly. That's an example, actually. It's literally lifted out of the CUDA programming guide, and there's an example in the CUDA toolkits, and we'll want to run those because it's a matrix multiplication. There's a naive implementation, and there is a implementation that's already hand-tuned with, with cache blocking and shared memory and so on, using all the tricks. And then for comparison, there's in the CUDA toolkit example, there's a sample code for that. There's a sample code also for using just CUBLAS. And then we can see what the performance difference is in using this hand-optimized code and the extremely optimized CUBLAS libraries. So, but if you're familiar with the matrix multiplication, so you have two matrices B and C, or A and B, and you want to store the matrix products in C. So we define pointers for the memory and the host. You allocate that memory, and with CUDA malloc, you allocate the same amount of memory on the GPU. Then, so I had that here. You get your values for A and B that from somewhere. I don't know. You have computed them. You read them from disk. I don't know where you get the data from, A and B. So the matrix arrays A and B. Once you have them, you copy them from memory to device with CUDA mem copy. So after that, you have the data sitting on the GPU. Okay. So that's just the device pointer, the host pointer. That's the size of the matrix, and this just tells that's part of the CUDA language specification. Is just a constant that specifies that you want to copy actually from host to device. Okay. You can see when you copy the data back here after the matrix multiplication, you have a variable called CUDA mem copy device to host for copying back. And then you set up the execution parameters. So that's the number of threads per block, and then that's the number of the grid in terms of that's constants. I didn't define those here, but that just means that's basically the size of your matrix. And then you execute the kernel with a number of threads per block and the number of blocks in your grid. And that's all you need. So the device pointers to the corresponding input and output values. And we'll look at the kernel, how it looks like in a moment. WA and WB should be the, so those are the dimensions of the matrices A and B, and those C. I think I have that on the next slide. Yeah, the width and the height. Okay. And so what you do in a matrix multiplication is basically, you have the product matrix C, where you multiply A times B. And, this output element is basically just a dot product of, this row vector and this column vector, right? And now, that for each element in this row, you'll have to read that row again, right? Over and over. Now you don't want to do that from global memory. So instead, what you do is you're tiling the data with some size of block row and block column for each block that is operating on that. And you effectively one time read the submatrix here indicated in yellow into shared memory. And then you operate with the data from shared memory when you do the matrix multiplication actually, okay? And that's very similar to cache blocking on a CPU code. So I think it's already 2:27. This is pretty tough to go through, but that's really, it's really, so what the code here does is exactly what I've been telling you. So you get an index into the global arrays A and B for each of the blocks, so you need to know which part you are operating on. You get that from your indices, those variables that I have been talking about before. And then what we want to do is we want to fetch really this sub block of matrix A, and then the next sub block of matrix A, and so on until we're done. And then we go into the next row. And then the same for the columns here on the matrix B. And then we compute the output here. And we fetch that data into shared memory, store the result in shared memory. Once we're done, we copy it back into global memory. And that's really what the code here is doing. If you can read that through and follow that through, you should be able to follow on that. There are some additional functions here that you can see here. For instance, we are allocating shared memory, right, of the corresponding block size, right? So AS, that's a float variable for A in shared memory and B in shared memory for those sub blocks that we are fetching from global memory, right? And here we load the data from global memory into that shared memory. Then there's a sync threads. You have to synchronize and make sure that all your threads are done fetching the data, because if you have more than 32 threads in your thread block, the first 32 threads, they don't know that the next 32 threads are done. So you have to add a synchronization here before you start working with that data. And then you just do the matrix multiplication. So then you just do exactly that dot product that I was talking to you about, and you store that in the C submatrix, okay? When you're done, you synchronize, and then you store the data back into global memory when you're done, okay? That's literally how you would implement cache blocking in the storing data in shared memory to optimize performance, right? So this is already pretty complicated example, using a variety of CUDA features, including two-dimensional grids and blocks, shared memory, and thread synchronization, right? And in reality, you wouldn't write the matrix multiplication because you want to use the BLAS function. But it's a very good example to look at. It's just to give you a hint at how CUDA code is written. It's not very hard, but you have to think about all those, where's your data in memory and how do you map that onto the GPU so that you can execute the operations in parallel. Now, how would you do something with OpenACC? This is interesting and pretty simple. And the interesting piece here is that we've learned something now about the memory hierarchies and so on, and we'll see how OpenACC can have pitfalls if we don't understand how this, hardware actually works. Okay, so we've looked at the tough stuff. So now let's look at the easier stuff. So that's OpenACC is a standard for expressing parallelism to be auto-generating code on to be executed on accelerator hardware, including GPUs. So it's similar to OpenMP if you're familiar with OpenMP. The nice thing is you have source code that still compiles for the host or for the CPU. If the compiler doesn't know the directives, it just ignores them, and you can get just like the regular C or Fortran executable. And yeah, so we have the PGI compilers for that. We also have them on Expanse, and we'll try that out. And I'll show you explicit examples here, so that's maybe more entertaining than what I've just been going through. You can get the OpenACC toolkit also here, and then there's just some changes happening that I'm actually also not, oh, sorry, here's the H too much. Some changes that I have not looked myself into is that at some point those PGI compilers are probably going to be phased out because NVIDIA has this HPC SDK, and so they have their own NVC compiler and NV Fortran that effectively are PGI compilers. Just, it's keep developing them and just don't call them PGI compilers anymore. In any case, so you get also a profiler with that and GPU-enabled libraries and some OpenACC code samples. Of course, OpenACC is not going to change independently of what compiler you use to compile it. Just to show you about all of that headache that we had with the CUDA, I mean, I've shown you matrix multiplication, which is more complicated, but if we look at the Saxby example, right? What that does, I told you, just does, on the left, you see, okay, this is C in Fortran. Let's just keep, I'm a Fortran guy, but let's just keep focusing on C because we had that C before. It's literally, you have that vector X and a vector Y and a constant A, and then that's what you do. You loop through all the elements of that vector and you just add A times X to Y, okay? Yeah, and now you add this Pragma ACC kernels, and that's all you need in principle for this to execute on the GPU, because then OpenACC, that's basically an OpenACC Pragma. And you see, this is just a comment. Unfortunately, you would have a begin and an end statement effectively to give hints to the compiler that, okay, this region here is what I want to have accelerated on the GPU. And here, the compiler figures it out itself because you have you're within that block of the for loop. Okay. Let me think about what else. Yeah, so that just means, yeah, you say ACC, you want to accelerate these by generation of a kernel. So, and that's just the directive syntax. Sorry, now Fortran is on the left and C on the right. But effectively, the way it looks like, you have Pragma ACC, or in Fortran, you have $ACC and then the directive. And then there are potentially some clauses. And then that's followed by a structured code block in C, or a matching end directive surrounding a structured code block in Fortran. That's basically it. And if you look at the kernel's construct, right, so here it has a code block. And then there are clauses that can have, for instance, if conditions, right? Or some other data clauses, and data clauses are quite important. With data clause, I mean, you can give hints to the compiler about the data that is being operated on, meaning, these arrays that they need to be uploaded to the GPU somehow, right? And then downloaded again once you're done with the computation. Compiler tries to figure out everything by itself, but it can't do this all the time. And for that reason, you have different data clauses. Okay. So here you have the directive, pragma ACC kernels, for instance, and then you can add a data clause, or you can use the data clause independently somewhere. And there's a list. List means, you know, a list of variables, for instance. And then you have copy, copy in, copy out, create, and present. And what that means is copy allocates memory on the GPU. That's the equivalent of CUDA malloc. And then copies the data from the host to GPU when entering the region. That would be the CUDA mem copy. Okay. And then it copies the data back to the host when exiting the region. Again, second CUDA mem copy. Copy in means, hey, well, that variable is input data, but don't copy it back, right? So you save on the copy operation. Copy out means, well, allocate the memory, but you know, don't copy it in because it's only output data. And create just, you know, creates memory for temporary data storage. Or present means, well, there's already data on the GPU from another data containing region in your code somewhere. Okay. And then there are a few other ones. Yeah, so we'll just look at an example. And if you still manage to follow me, we'll look at a Jacobi solver. In this case, you know, we want to converge that solver to a given threshold. What it does is basically, as an example, it could be used to solve the Laplace equation in 2 dimensions, and literally numerically how it looks like if you have a 2-dimensional grid, for instance. The next iteration basically gives the value of each grid point is just the average of the neighboring grid points. Okay, so K is an index for the iteration in your loop. So you know, I have values, say temperature gradient on my 2-dimensional grid, and so you just sum the values of the neighboring grid points here and divide it by 4, right? So that's the average of the neighbors, and you iterate that until the values don't change anymore within a given threshold. Okay, so that's the algorithm that we want to implement, and here's a C code that does that. So we have a big while loop out here. So we iterate as long as our error. So the error is the difference of, you know, matrix elements between 2 steps is larger than our tolerance, and as long as we didn't hit a maximum for our number of iterations. Okay. And so what we then do, so that's just the serial CPU code, right? So we go through all our grid points, J and I, and then we compute the new output data as a quarter of the sum of the neighboring grid point data, right? Just like what I showed you in the slide before. And the error that we have, so that's the convergence check, is basically the maximum difference between what we computed as the new value and the previous value, right? And so when we are done with that updating, then we swap the output with input data. I know this could be done better with just, in particular in C, straightforward with swapping pointers, but here it's done via a memory copy operation. So this clearly can be improved, but it's just a simple example. And then we increase our iteration counter, and we'll stop once our error is smaller than tolerance, or once we have hit the maximum number of iterations. Okay. So really here the compute happens when we want to do that in parallel on the GPU, because we might have many grid points. And I told you, right, you can say pragma ACC kernels. You say, you tell the compiler, well, just parallelize this on the GPU for me, right? Write a kernel that does that. And so that's what you could try. Then you use, for instance, the if you have the Fortran code, you use PGF90. That's the Portland Group Fortran 90 compiler. The example that I've shown you is C. That specific example, both C and Fortran code, is on the website, the course website, and we want to try this also on Expanse, and I'll see if I can get that compiled and run for you as well. Right, we'll look at this together. In any case, so if you have the C code, you call PGC, I guess it's called PGCC. I don't remember off the top of my head. And then you use the -ACC flag. You want OpenACC acceleration. This you don't have to specify anymore. That's basically the target architecture NVIDIA. That's default now. And minfo just gives you some additional information like that's what we see here. So we compile this code and we want the output in this executable here, okay? And then it gives you some information, right? It tells you literally it's generating copy out, copy in of the different arrays. And in this case, I had an array size of 4094 elements, 4094 by 4094. It finds a loop that is parallelizable, another loop that is parallelizable. So those were the 2 for loops, and it generates a kernel for that. And there's something called like gang and vectors, and that is basically OpenACC speak for grids and blocks. Okay. Then it does a reduction operation here for a max reduction for that error, because that error is computed for all the different threads and the blocks at the same time, and then we need to do a reduction operation to find the maximum value. Does another copy in and copy out, and then it finds the other parallelizable loop that is the update of the matrix. So this was the first parallelizable loop, right? Double loop, and then the second double loop. And now what I did here is I went on Comet. This is timings for the Tesla K80s, apparently. Okay. I also had some timing somewhere for the P100s, but it doesn't matter. The story is always approximately the same. The CPU code, there's also an OpenMP parallel CPU code that instead of the OpenACC, Pragmas has OpenMP Pragmas to parallelize across multiple CPU cores. And so you can see, you go from 1 thread, CPU thread, to 2. You get a speed up of 2, and then on 4, you get a speed up of 3, on 6, a speed up of 4. So it's not ideal, but I mean, just for inserting a simple OpenMP Pragma, that's quite neat. Now the OpenACC GPU code is super slow, right? So the speed up versus the 6 cores, it's basically 500 seconds, right? I mean, it's something went wrong. So what's going on here, right? Now, you can profile that either with a PGI profiler, or you can set this environment variable that activates profiling and spits out information to the standard out to your shell. And so that's the output that you get. And there's some things to note. It says here data region has been reached 2,000 times. Data copy and transfers 8,000 times. That took 22.5 seconds. So this time here is in microseconds, right? And it's like, wow, 22 seconds spent on data copies, right? And then the compute region, well, it just took 1.5 seconds for the compute. So you spent all the time copying data forth and back. And you can clearly see that something went wrong because we spent all the time with data transfers between host and device. And that's what I was telling you. If you understand a little bit about the architecture, you need to always know a little bit about the architecture to know what's going on. And the compiler just wasn't smart enough to understand that it doesn't always have to copy the data forth and back after each iteration. So every iteration of the outer while loop, we basically have copied the results. So, we have this while loop. where we update our matrix. And we should keep doing that until we are converged, but instead, after every step of the compiler-generated code, that does a CUDA mem copy. And that happens between the host and the device, right? And like I said, that's very slow. It goes through the PCI Express bus. So we have to help the compiler and tell him, look, here's an OpenACC pragma, a data clause, and do the copy of A before you start that while loop, right? And create a new, right? So just create that a new. We don't need to copy it forth and back until we're done with that while loop, okay? So copy it in at the beginning of the loop and out at the end. And allocate a new on the accelerator. And by adding that, now it looks much better, right? So we have the time down to 5 seconds. So now we are 3.4 times faster than 6 OpenMP threads on that single GPU. Okay. So that I would say is a success, given you've just inserted 3 lines of pragmas into your source code, and you have code that still compiles for the CPU. And so you're down from 69 to 5 seconds, so 69 seconds on a single core. And that's mostly what I wanted to tell you about OpenACC, just a little bit more. It gives us more detailed control over the parallelization. You have game worker and vector clauses that map basically to grids and blocks. So gang corresponds to a block. So you can specify, you know that it can share resources such as cache. And then you know that the vector threads, they work in lockstep. So that's basically the size of a warp, and you can exploit that in certain cases if you know what you're doing. And that just basically means by understanding more about OpenACC execution model and the GPU hardware organization, you can get higher speed ups on the code, right? And if once you're done, of course, you should profile your code, and then you can often reorganize the code for higher performance. That holds both for OpenACC and for CUDA code, of course. And it's very often the case, you will have to restructure data types so that you have stride 1 access and to data elements. Not always the case that you can simply insert OpenACC pragmas and it will execute on your GPU, but it might just not have great performance. But in general, it's pretty easy to do. Then when do you want to do that? So nested for loops are best parallelization, right? Something like we saw, double for loop, for instance, right? Lots of floating point operations. Large loop counts are needed to offset GPU memory copy, right? If you have a loop that iterates only over 10 elements, the time that it takes to upload the data and download is just larger than the compute that you're doing. So you want to have sufficiently large, say, matrices or arrays or grids or whatever you're operating on. And the iterations of the loops must be independent of each other. And so you can help the compiler here either with clauses, independent clauses, or you've seen that. You might have noticed that I used the restrict keyword in C in one of the examples. And the compiler must be able to figure out sizes of data regions, and you can use directives, to explicitly control the sizes if that's not already directly available through the source code. Pointer arithmetic is not good. So, and the function calls within an accelerated region must be inlineable. So, if you have a double loop and then you have a function call, it calls another function inside that does, I don't know, a lot of things, that can't just be easily, the compiler won't be able to generate a kernel for that. Okay. Then use the time option to learn where your time is spent, right? Like I showed you before, you might be spending all the time on memory copies that are not necessary. Yeah, eliminate pointer arithmetic, inline function calls in directives regions. You know, if you have multi-dimensional arrays, make sure that, you know, your memory access is contiguous. Then use data regions to avoid excessive memory transfers. And there's also option to use conditional compilation with an OpenACC macro, depending on whether you compile with OpenACC or not. And yeah, so that's all I wanted to tell you about OpenACC. You know, we're pretty far in with the time. This is information about Comet that's not very helpful anymore because Comet is going to be decommissioned. I unfortunately did not have time to update those slides. I think Mary told me that she added some information about expanse here, but I don't see that.
Yeah, there should have been a slide in there on the expanse architecture. That's interesting.
Oh, I don't know.
Sorry about that. Those should have been at the beginning.
Okay.
And those slides were not updated. I don't know
Yeah,
why.
I'm sorry for that. But
that's okay. That's okay. We can fix all that. The main information was in the guts of what you were presenting anyway. So
yeah, let me just so we have about a little less than 10 minutes. So I'm sorry it took very long, but I hope it was informative. But let me just do so. Can you see that terminal here?
Yeah.
Okay, so
maybe make the font a little bit bigger for the purposes of recording. We tend to need a lot larger font.
Yeah, I already.
I think how's that look, Jeff?
That's okay.
Okay. Cool. Usually I was used to get some information about expanse when logging in. Anyway, so yeah, this was just logging in. So now I'm logged into expanse, and so the question is, how do you get started on expanse, right? And how do you get onto GPU nodes? And I believe, Mary, we're going to update some of the information that's online at the on the repository for the course, right? Let me also, I think I have the web browser here. Sorry, that web browser size is now very relatively small as well.
So but
that's the HPC training website, and there should be some information here, right?
Yeah, and there's some examples that are, I'm trying to test them and debug them, but that are working on the week 3 examples. The OpenACC example has been tested on Expanse, and I'm adding to the Expanse 101 examples and moving them over to here. And the GPU code examples are not vetted yet. They're pulled from the repository. So
okay, so but in principle, if I go to code and copy,
yeah.
I should be able first of all to clone that repository. Oops, let me move this away here again. Okay. So this has generated the directory HPC training. And then we have the week 3. And so this is still in flow and being updated, but right. So let me show quickly what's in GPU code example. So we have CUDA samples. Let me look into that because we looked into CUDA samples first, and let's see what's in the README file. Right, so this is, yeah, okay. I don't know 100% if this is all working like that, so I haven't tested it, but we have to update some of those things from Comet to Expanse. But there's some information about what's in the directories and so on. And there's different things I wanted to show you about CUDA samples. But let's look at the CUDA samples that I have here. These are very simple samples that I didn't go through. but you can have a look at them, right? So there's something that is an addition, for instance, in a vector addition. So if we go into this directory, there's a vector addition on the GPU. This just adds 2 numbers. This is a vector addition. So you can just look at the CUDA code, and this can get compiled with the NVCC compiler. And the exercise in there is basically literally just that code with something left out to fill in. If you look at the source code. So these are very simple examples. And then I would encourage people to look at the CUDA toolkit samples. I'll try to show you how to get to those. Before doing that, there is also there's the OpenACC samples, and so there's the SAXPY example that we went through, and the Laplace2D, that's this Jacobi iteration, that's the Laplace solver that I just talked about. Okay, so that's the one that I used to get those timings on Comet. And as you can see, so there's a README file as well that tells you how to compile those with the PGI compilers. There's the corresponding C and Fortran codes. And you can see the version 1, that's the first version that doesn't have the data clause, that doesn't run very efficient on the GPU, and then there's the optimized versions. And the corresponding OpenMP version with the OpenMP pragmas to run in parallel on the CPU. I'll try and see if I can get to compile those, but I wanted to show you also how to get access to the compute nodes. And we will update that information on the website. So for interactive access, let me copy this. This is just from my own notes here. Sorry, this was wrong. So the command is basically srun, and you can get onto the regular GPU nodes, or their specific debug nodes. Then there is a partition that is called
Andy?
Yes.
Andy? In the directory, the folder above, you have the script for aliasing get GPU. I updated that last night, so that should work.
Okay. Okay, let's try if this works.
Get GPU.rc.
Okay, so that's basically
it has the class account. The only problem I'm seeing today is the 3-hour time limit appears to be invalid for our charge number, but let's see if it works for you.
Okay, so let me try get GPU. I'm not sure I'm part of that account. Not enough.
Yeah, change the account number. You should be in it. I can add you, but not right now.
Yeah, let me
30 minutes seems to be okay, and change the dash account. Passing the account is something new on Expanse. It has to be in the srun and also in the batch scripts. So just as a side note, folks, in the Expanse 101 tutorial, I have examples for GPU compiling, and there's some batch scripts in there you can take a copy and try and make them work.
Anyway, so what this does, it runs srun, it gets you one node, one task per node, CPUs. So you get 10 CPUs. There's a GPU node has 4 GPUs and 40 CPU cores. So you should not ask for more than 10 cores, but you only ask for a single GPU. Here you're asking for a single GPU and on the shared GPU queue, okay? And so let me try to see if that works. Yeah, so now you see I'm on a not on the login node anymore. Now I am on that Expanse compute node 758. Okay, and there's a command that's called Nvidia SMI. So these commands are actually similar. Those commands, they're the same on Comet, right? So the information that's on the slide currently is still available, is accurate. So the system management interface, it gives me information about the GPU on that system. And you can see there's now one GPU available. That's a Tesla V100 SXM2. All right. And now I can use that. On Expanse, we also use modules. Currently, I have CPU module loaded, and GCC compiler. I don't have the GPU compilers loaded and the libraries and the toolkit that I need to run GPU code. So that's something I need to do. Do we have that in there as well, Mary?
I'm sorry, what?
There's no RC file yet in these examples for loading the modules for GPUs, right?
In the Expanse 101 examples, I think if you're asking the module environment to go into OpenACC, cap the README file.
Yeah, I was going to do that also for CUDA, but that's.
So if you go up to the top, there are the 4 commands for loading the environment for PGI compiler. And then it's I'm uploading vector addition and a couple of simple ones for CUDA to load the CUDA compiler. But it's
yeah,
the same kind of pattern.
Okay, so for CUDA, I know that. Let me do this. So module load GPU and then module load PGI should load module specific for GPUs and then PGI. And if I say module list, in fact, it's true, I have the PGI module loaded, and then, oh, that's not there. Did they rename the compilers? PG, oh, so it's called PGF90, sorry. Right. So PGF90 is the Portland group F90 compiler, and then PGCC is the C compiler. So I also have, I had some information. Oh yeah, GPU modules for RC. This year we'll load the CUDA toolkit. And now I have, for instance, an Nvidia CUDA compiler, NVCC available. Okay. So with that, for instance, though, if I go to the GPU code examples, let me go to the CUDA samples. And yeah, we'll just do the additions. And I think I should have information here in the README file. I do. Okay, let's just do NVCC vector at GPU, one of those, and see what happens. Okay, did compile the code. I got a file here, a.out, so of course I can give it a different name. And let's see if it actually runs. It runs, okay. So what that did, it did a vector addition of a, just a very simple kernel. If you look into that code, that has a certain number, I don't know what is this, 1 million elements. And I launched 256 blocks and 128 threads per block. So basically 32,768 threads in total, and did a vector addition, and that actually executed on the GPU. So if I look into that vector at source code, you see I have here global void add function. That's actually the add function that I showed you at the very beginning. And then I had a main program here in C that allocates, host and device memory, initializes the vector on the host, does a CUDA mem copy from host to device, and then it calls that add vector here within a certain number of blocks and threads per block. And then I check the results because I know actually what the computation does, and I just check the output data that it actually computed the right values. Okay, so that just shows that vector addition works, and it just executed on the GPU. There are CUDA code samples. That's something you should look at. Now I loaded the CUDA module that defined an environment variable called CUDA home. And so, I'm sorry that we don't have that automated, but there is actually a directory here in VM shared apps CUDA 10.2 SDK 10.2.89, right? And these are CUDA code samples, and so there are different code samples like simple utilities, graphics, and so on. Let's look at simple. There are simple code samples. There's, for instance, a matrix multiplication, and so that matrix multiplication example here should be the matrix multiplication, more or less what I went through, and this is the one with CUBLAS. So we could copy those into your home directory somewhere. See if this works. If I can just copy this here. Okay, simple. What's it called? Matrix. Sorry, got the name. Oh, matrix one. Okay. And I should be able to compile that just by typing make. There's a make file. You can look into the matrixmul.cu. So these samples are very instructive to look at and read and look at source code actually, right? And then you can execute that. So this generated an executable. And if I execute this, you know, it finds the device, it knows this is Volta architecture, and then you know you have these matrix dimensions, and it launches it does a matrix multiplication for those matrices. C is A times B, and we get a performance of, well, not bad, right? 3 teraflops. Okay. Now let's try and see what happens if I go to matrixmul CUBLAS. It's effectively here source code that instead of explicitly implementing the matrix multiplication, just does a call to the CUBLAS function for matrix multiplication. And let's have a look. So code is compiled. And let's run this. And as you can see, so this gives us 7.5 teraflop performance, so approximately double the performance. So, so if you can, just don't implement something like that yourself, unless you know it's just for learning purposes, of course. And finally, I know we're over time. If you want, I can try to see if I can get the OpenACC example compiled.
That's okay. So go ahead. Some people are dropping off, but that's fine.
Yeah. So thanks for everybody who has been hanging on so far. And so GPU code examples, OpenACC samples. Let's look at the README. There's some information in there, for example, right? So we could try to compile so this is the serial code. Here we have the OpenMP code. Let's try. Shall we try? I don't know, the C code, or it doesn't really matter which one we pick. Let's pick the Fortran code. That's vanilla plus 2D. And let's see if this compiles. So this is on the GPU, right? And not on the GPU. So this is the OpenMP source code. And so this has the -MP, so the OpenMP flag for the PGI compiler. So I should have this executable here. and I could do something like export one key num thread equals, I don't know, 10. That's the number of cores that we have available that we requested, and run that code. It is pretty quick, as you can see, but it's using 10 compute cores, CPU, and so it took 7 seconds for 1,000 iterations of that plus. I think that's the error in our algorithm, right? Remember, I was talking about go until the error is below a certain threshold, or we reach certain number of iterations, and we set that to 1,000 in the source code. If you look into the source code. Now let's look at the Jacobi ACC. So that's again effectively compiling exactly the same way with PGF90, but now we compile the source code that has the OpenACC pragmas, right? If you want, we can do the V1 first, but let's just directly use the optimized one that has the data clause in the source code. That's literally the source code that I just showed you. And we are having the -ACC flag, and we get some information about what the code is doing, right? So that's exactly what I was showing you, right? I mean, it finds these loops that are parallelizable and so on. And all we have to do now is to run this, and it should run on the accelerator. And boom, it took 1 second. Okay, so 10 CPU cores took, what was it? 7 seconds, and the Volta GPU took 1 second. So I would say pretty good speed up, 7 times as fast. It gives you the performance of 70 CPU cores on the single GPU. Everything works as expected. So I hope that has shown you a little bit, how to, how CUDA code and OpenACC code is developed, and how you maybe can get started with your own code, and how you can compile something on Expand, and how you can run the code. So once you have code that has been compiled with NVCC or OpenACC pragmas and so on, it will automatically run on the GPUs. You always have to load the toolkit so that the libraries that the source code, that the executable depends on, works, but other than that, it will automatically run on the GPU. And yeah, so that's all from my side. With that, I would like to thank everybody for joining, and I'd be happy to answer questions if there are any questions. Thank you.
Thank you, Andy. That was great. Anybody have questions? So Andy, while people are thinking of them, I think we'll put the link to the CUDA toolkit onto the README file for week 3. And I'm impressed, and whoever might be joining us from the systems group, they did a great job I'm impressed how it made the toolkit compile, and so far every example you've shown us is working. So the installation guys did a great job. So you guys can with confidence grab that toolkit and start playing with it. Sorry.
Yeah, everything works. I mean, I've tested the machine before, with our source code and so on. Everything, the quantum chemistry code that we're developing, and everything's working great. It's just, the setup is a little bit different from Comet, so the way for you to find which modules you have to load and so on, you might have to look it up on the Expand. I mean, it's all documented, so I hope that there are no glitches along that way.
Right.
So is anybody monitoring the chat or anything? I've not been doing that. I don't know if there's.
Yeah, there is one question.
Go ahead.
How do you run a container with GPU, and how to set the drivers automatically?
Oh, good question. I know close to nothing about containers. So I defer that question to somebody who has more experience.
I'll step in. We have a training session, I think after the break, we have several sessions in the winter quarter. And one of our first sessions in the spring quarter will be containers. If you look ahead at the schedule, we'll address that. It's very doable. And we have examples in that CMS share apps directory that Andy shared with you earlier, but we'll address it formally in our training series after the break.
Yeah, I think the question with that, and probably there have been, there are certain issues with, the driver is installed by the operating system. So even if you have, the CUDA toolkit in your container, you might need a different driver. Although typically that's not an issue because the driver is specific to the hardware and the hardware doesn't change.
Yeah, so Marty Candace is our container person, and he does a lot of Singularity. And the model on Expanse and Comet is we'll provide a sample set of working containers, for example, or others code. And you can work with that, or you could get the formula from Marty. He has all of that stuff up on a website. And if you want to get to it right now, you could email him. But all the container buildings formulas that he used is on a website that you can take that, copy it, and build your own. The containers take a long time to build, so ours will be some minimal set, but a pretty robust set that you might need for GPU computing from a Singularity container. I don't think at this point we're doing other containers. We don't do Docker, so we just do the Singularities.
Yeah, that's very typical for HPC centers that Singularity containers are supported, but not Docker.
Yeah.
But that said, I really don't know much about containers, but I mean, there's a straightforward way of converting Docker to Singularity containers, as far as I know.
Could I ask a question? When you were saying benchmarking simulation dynamics, right, versus density functional calculation, the second one is so how do you compare it with the same accuracy? Like, when you were solving the equation in these last few examples, like the Laplace equation, you have a way to stop it and know that this is the accuracy you have. So, but for simulation, how did you do that so that they are comparable?
So with simulation, you mean if you have a simulation where you don't have an exact answer? I mean, so
yeah, no, you did dynamics, right? But I call it simulation, but you probably
right. So yeah, exactly. So for instance, you're right. So for the density function theories, it's pretty clear cut, because we know numerical accuracy and we can converge the SDF, and we have very, very good proof about that. For molecular dynamics, it's a good question because it's in some sense chaotic, right? And if you have a parallel computation, your trajectory will take different, can diverge with the correct trajectory because, all that counts is basically, ergodic hypothesis that if you run long enough, you sample the correct state. So the only thing that there's two things you can do. One is, you can check energy conservation, that your forces are sufficiently accurate. The question is, how accurate do your forces have to be, if you have a thermostat on or similar things. So the only way to do that is to have a sufficient large number of, and that's what we did with the molecular dynamics code. Simulation ensemble of simulations improve that the ensemble quantities that we compute are coincide with the expectations that we have from our double precision implementation that we had beforehand.
Thank you. Thank you for introducing me to GPU. It's very educational.
Yeah. Okay. Yeah, you're welcome.
Well, okay. I think with that, we can conclude our amazing GPU session. And we'll see you guys next week for GPU CUDA with Python computing. So that should be a whole lot of fun. And we'll see you guys soon.
All right.
Thank you.
everybody.
Thank you, Andy, so much. Really appreciate it.
Sure, you're
Thanks,
welcome.
Andy. It was great.
Yeah. Really nice in-depth technical presentation. I appreciate it. Okay. Bye, guys. We're
Yeah,
going to leave. Jeff, you can stop recording now.
Bye, everyone.